Good evening, everyone. I'm Anesh Ambikar, PMRF and PhD candidate from Aerospace Engineering, ISC Bengaluru. Welcome to the Week 6 interaction for the NPTEL course Engineering Mathematics 2. This course has the code NOC 23MA25 and is conducted by or taught by Professor Jitendra Kumar from IIT Kharagpur. In this week, we learned about different concepts such as Weierstrass's approximation theorem. We learned about interpolation, how what different types of interpolating polynomials there are, or different interpolating schemes, which includes Lagrange interpolation. We also learned about the finite difference operator, how it ties into creating the Newton's forward difference, backward difference, or divided difference scheme. And we also, before all of this, touched upon how Taylor series expansion is quite different from interpolating for a polynomial over the entire domain. Then we moved on to numerical integration where we studied the Newton Cotes scheme under which we looked up different rules such as trapezoidal rule, Simpson's rule, and we also studied the weighted mean theorem and discrete mean value theorem. With this all content in mind, as is the practice for every week, we have selected a set of few curated questions which try to cover as much of these topics as possible so that it can further elucidate the concepts which have been taught in this week. Let us move to the first problem. The statement is, suppose f of x equal to e raised to x square plus cos of x plus logarithm of 1 plus x square, where x belongs to 1 to 100. Then we are asked to find which of the following statements is or are true. Okay, by Weierstrass's approximation theorem, we have this condition. I'll write the statement. We have this condition where suppose we are given a function f of x which goes from the domain A to B to the real, and we are given that this f of x is continuous. Then what this means is that for all epsilon greater than 0, there exists a polynomial approximation p of x such that modulus of f of x minus p of x is less than epsilon for all x belonging to A to B. So this is the statement. You can see that for our case, we essentially have, f of x equal to e raised to x square, this cos of x plus log of 1 plus x square. This is comprised of three different terms. E raised to x square, this we know is continuous for all x belonging to our domain 1 to 0. Same is the case for cos of x. Same is the case of logarithm of 1 plus x square. So this will go from log of 1, which is 0, to log of 10,000. With this in mind, we can clearly say that since all the three components which are summing up or adding up to create the function f of x are continuous in the domain 1 to 100, f of x itself is continuous in the domain 1 to 100. So which implies that we can apply Weierstrass approximation theorem. So in our case, what this also means that we can choose a certain epsilon value. So suppose if we choose epsilon equal to 0.01, then we end up with the first statement, which is there exists a polynomial p of x with the property such that modulo of f of x minus p of x is less or equal to 0.01 for all x belonging to 1 to 0. So here the only thing is epsilon is equal to 0.01. Same thing you can see in the second statement, which states that there exists a polynomial p of x with the property modulo of f of x minus p of x must be less or equal to 0.0001 for all x belonging to 1 to 100, which gives us epsilon equal to 0.0001. Third statement states that there doesn't exist a polynomial with the property f of x less f of x absolute value of f of x minus p of x to be less or equal to be less than 0.03. So this violates Weierstrass approximation theorem, because here we can plug in epsilon in equal to 0.03, and with that we essentially see that the statement C is false. So only statements A and B are true, which gives us this as our correct answer for this particular problem. So this covers a case for the Weierstrass approximation theorem. Problem number 2. A certain function f defined on the interval 0 to 1 is such that f of 0 equals 0, f of half equals minus 1, f of 1 equals 0. So and I'll just plot. So suppose this is my x, this is my f, this is my y. If I take y equal to f of x, what I'm essentially getting is this is my 1 point. I'll label this as minus 1. These are my 3 points. And we are asked the quadratic polynomial p of x, which agrees with f of x at 0, half, and 1, is minus 4x plus x square. This is easy to check. You can just see that p of 0 equals 0, which is f of 0. P of half equals minus 2 plus 4 into 1 by 4, which is minus 2 plus 1, which is minus 1, which equals f of half, and p of 1 equals 0. So f of x agrees, so p of x agrees with f of x on the points x equal to 0, half, and 1. And we are told that if the third derivative of f of x is always less than 1 in magnitude, less or equal to 1 in magnitude for x belonging to 0 to 1, then we are asked to comment on f of x minus p of x for the general x. So you can see that this is for general x belonging to, or rather for all x belonging to 0 to 1. Okay. So how do we do it? We first write the error as, or the residue as, rs of x is modulo of f of x minus p of x, which in our case will be equal to x minus 0, x minus 1 by 2, and x minus 1 whole times modulo of f triple dash of epsilon by 3 factorial. Okay. So this is the error that we obtain in an interpolating polynomial. So I'll just write this. Error in interpolating polynomial with distinct n plus 1 points. So with this in mind, and here we have to note that this epsilon belongs to the so x in our epsilon belongs to the smallest interval which will contain all the points given. So smallest continuous interval which contains x equal to 0, x equal to half and x equal to 1, which in our case means that epsilon belongs to 0 to 1. So in our case, the residue would look like, or the error would look like, Rs of x has to be less or equal to modulo of x, x minus 1 to x minus 1 modulo of this by 2, and this 3 factorial will come, so 2 into 3 factorial, which is 2 into 6, so we end up with 12 times 1. This is because we have been given that the third derivative is less or equal to 1, right? So okay, and with this in mind, I we look at couple of more points. First is modulo of x into x minus 1. This is always less or equal to 1 by 4 when x belongs to 0 to 1. Okay, and the second thing is modulo of 2x minus 1 is less or equal to, so this will always be less or equal to 1 when x belongs to 0 to 1. With this in mind, you have a residue which turns out to be modulo of 1 by 12 into 1 by 4 into 1. So this whole thing will always be less than 1 by 12, 1 by 48, sorry. So in our options, 1 by 48. So if Rs is less or equal to 1 by 48, it automatically means that it is less or equal to 1 by 12, which is option number A. Problem number 3. If f of x is a polynomial of second degree, then which of the following options are correct for a small step size h? Okay, so we are asked to comment on, if you look through the options, we are asked to comment on few different things, such as the second difference, the third difference of f of x, and whether it is a constant, whether it vanishes, or if it is a polynomial of order 1. So it is given that f of x is a polynomial of degree 2, which means that in general f of x is equal to ax square plus bx plus c. Now we take the first difference, that is nothing but f of x plus h minus f of x, which is a times x plus h whole square minus x square plus b times x plus h minus x plus c minus c, which if you simplify it turns out to be a times 2x h plus h square plus bh. And if we take the second difference, I just rearrange these terms, they essentially become 2ah x plus ah square plus bh. If I take the second difference, it is nothing but first difference of x plus h minus first difference of x, which is 2ah x plus h minus x plus ah square plus bh minus of ah square plus bh. These two cancel out, and here also an x cancel out, so we essentially end up with 2ah square. So this tells us that the second difference of f of x is constant, which in turn means that the third difference of f of x should be 0, or it should vanish. So options A and B. Problem number 4. Which of the following are Newton's forward difference interpolating polynomial based on which of the following are Newton's forward difference interpolating polynomial based on four nodal points x0, x1, x2, x3. Here xr is equal to x0 plus rh, where h is the length of each space and r is an integer varying from 0 to 3. Okay. So we are asked about Newton's forward difference interpolating polynomial. It is given as, so we have if you look at the options, there are, we can quickly rule out option number C and D, because instead of the forward difference they have the backward difference characterized by this nabla symbol. So this backward difference, so both of these options are out. Option 1 and 2 contain the forward difference and therefore require another look. For Newton's interpolating polynomial, we have the expression which is given as Pn of x plus hu. This is equal to f naught of x plus x minus x naught. First difference about f x naught of h plus x minus x naught into x minus x1 by 2h square grad square f plus so on. So if we take the third term, it is x minus x naught, x minus x1, x minus x2 grad cube f naught. Sorry, third difference, not grad, third forward difference about f naught times 3 factorial, which is 6 h square. With, so this matches up with our first option. If we now substitute u is equal to x minus x naught by h, we essentially have u minus 1 to be equal to x minus x naught minus h by h, which is nothing but x minus x1 by h, and u minus 2 be equal to x minus x2 by h. Similarly, you can follow it from here, which essentially gives us our forward polynomial to be f naught plus u times forward difference f naught plus u into u minus 1 by 2 factorial, which is 2 times second forward difference of f naught plus u into u minus 1 into u minus 2 by 6h, no, 6 into third forward difference of f naught. This is essentially option number B. So that settles up this particular problem. For fifth problem, we are asked to find a polynomial of degree 2 or less which takes the following values. So at x equal to 1, it should take 0.11. At x equal to 1.5, it should take 0.15. And at x equal to 2, it should take the value 0.16. And we are asked to use Newton's interpolation formula. So from this particular example, we want a second degree polynomial. So it is f naught plus u times first forward difference of f naught is u into u minus 1 by 2 times second forward difference about f naught. In our case, f naught is equal to 0.11. U is x minus x naught by h. For this case, you have h is equal to 1.5 minus 1, which is also 2 minus 1.5, so equal to 0.5. So this is twice of x minus 1 and u minus 1 to be equal to x minus x2, sorry, x minus x1 by h, which is nothing but twice of x minus 1.5, which is equals, so this is 2x minus 2, and this equals 2x minus 3, and we have grad of f naught, sorry, forward difference of f naught to be equal to 0.14 minus 0.11, which is 0.03, and second forward distance of f naught to be equal to 0.16 minus 0.14 minus of 0.14 minus 0.11. So this is minus 0.01. So in our case, the polynomial P2 of x essentially looks like 0.11 plus 2x minus 2 into 0.03 plus 2x minus 2, so twice of x minus 1 into 2x minus 3 upon 2 times minus 0.01. So this is 0.11 plus 0.06 x minus 0.06 minus 0.02 x square. This is x minus 1, so minus 1 into 2 minus 2 minus 3 minus 5 into minus 0.05 x, and 1 into 3 into 0.01 into minus 1, so that is 0.03. So if you look at it, we essentially end up with minus 0.02 x square plus 0.11 x and 0.11 minus plus 0.02. So this is essentially our option number A. Problem number 6. We are now using Newton's backward interpolation to find the interpolation formula, as well as then plug this up into to find function value, estimate the function value at x equal to 1.5. So in this case, you can see that h is nothing but 2 minus 1, which is 3 minus 2, which is 1. And my backward formula would look like x is f2 plus x minus x2 by h, backward difference of f2 plus x minus x2, x minus x1 by 2h square, backward difference, second backward difference about f2. So my backward difference about f2 is nothing but 8 minus 1, and my second backward difference about x2 is 27 minus 8, which is 19, and my 7, so this is 12. Substituting the values here, we essentially end up with 2 is equal to 6x square minus 11x plus 6, and if you do P2 of 1.5, which is nothing but 6 into 2.25 minus 11 into 1.5 plus 6. So this is 6 to 12, 13.5 minus 16.5, so minus 3 plus 6, which is 3. So we end up with option number B. So using Newton's backward interpolation formula, we calculated a second order polynomial approximation for f of x, which we then use to approximate the value of f of x at x equal to 1.5, which ends up being 3. Problem number 7 asks us to find Lagrange interpolation polynomial for the given data points. So our Lagrange interpolation polynomial PL of x is nothing but of the form summation Li f Li of x into f of xi. Here I will go from 1 to n. In our case, n equals 3 and else f of f0, which is nothing but f of x0, is equals 1. L0 of x equals x minus x1 into x minus x2 upon x0 minus x1 into x0 minus x2, which gives us x minus 1 into x minus 2 upon 0 minus 1, which is minus 1, into 0 minus 2, which is minus 2. So we end up with this being half of x square minus 3x plus 2. Similarly, if we calculate f1 is given to be 2, if we calculate L1 of x, that is equal to x minus x0, which is x minus 0 into x minus 2 upon 1 minus 0 into 1 minus 2. So this is 1, this is minus 1. So we have minus x square plus 2x. Finally, if we took L2 of x, it's nothing but x minus 0, x minus 1 upon 2 minus 0 into 2 minus 1, which ends up being half of x square minus x. F2 is given to be 11. Therefore, my Lagrange polynomial ends up to be 1 into 1 into f0 into L0, which is 1 into L0, which is half of x square minus 3x plus 2 plus twice of, you have minus x square plus 2x plus 11 into half of x square minus 2x, x square minus x. So if I take this half outside and write all the terms, you have x square minus 3x plus 2 minus 4x square plus 8x plus 11x square minus 11x, which turns out to be, so this is x square 12 minus 4, 8 x square by 2. So this is 4x square. About the x term, so you have minus 3 minus 11, so minus 14 plus 8, which is minus 6 by 2. So minus 3x and plus 1. So 4x square minus 3x plus 1 is our interpolating polynomial, which is given in option C. Problem number 8. Find in the following table which of the, given the following table, which of the following options is correct. This should be given. So we are given f of x, x and f of x, and we are asked to find what which of the following options given below are correct. So if you look through the options, we are essentially looking at the divided difference f2 comma 1 and the divided difference f3 comma 2 comma 1. So we'll first start with the easier one. F of 2 comma divided difference of 2 comma 1 is nothing but f of 2 minus f of 1 upon 2 minus 1. So f of 2 is 15 minus 8. Oh, okay. So here 3 to 1, they correspond to the point numbers, not. So this is, I should write this is x1, this is x2, this is x3. So when we say f of 2 comma 1, what they're actually referring to, f of x2, x1 and x2 minus x1, which is f of x2 is 8, x1 is 1 upon 1 minus 0. So this is 5, which gives us option B. Then we look at divided difference between x3 and x2. which if you plug in the values turns out to be 15 minus 8 upon 2 minus 1. So this is 7, and now if you take the divided difference between these, it's nothing but 3 2 minus f of 2 1 upon 3 minus x1. So this is 7 minus 5 upon 2 minus 0. So 2 by 2, which equals 1. So option A. This was a problem on divided difference. Problem number 9. So far we have covered problems for on interpolating polynomials, which started with approximation theorem, calculating the residue or error between actual polynomial and interpolating polynomial with finite difference operators, forward difference and backward difference polynomials, then divided difference, and as well as Lagrange interpolation polynomials. Now we are moving to numerical integration, specifically trapezoidal rule, which is which comes as which comes under the types of rule, all the rules uh, which are collectively called as Newton Cotes formula. So in trapezoidal rule, we essentially, when we are given to integrate between a and b f of x dx, we assume like a trapezoid between a and b, and that gives us this as our trapezoidal area. So in our case, f of x is nothing but 1 by 1 plus x, a equals 0, b equals 5, which means f of a equals 1 upon 1 plus 0, so which is 1, and f of b equals 1 upon 1 plus 5, which is 1 by 6. So my integration is approximated as 5 minus 0 by 2 into 1 plus 1 by 6, which is 5 by 2 into 7 by 6, which turns out to be 55 by, oh, I think I made a mistake. Oh, yeah, I made a mistake here, sorry. I assume that we have trapezoidal rule acting over the entire interface as one particular in only one interval, but what we actually have is I forgot this, we actually have this data. So we have been given an interval size. So notice that since h equal to 1, number of intervals is nothing but 5 minus 0 by h, so which is 5 by 1, which is 5. With this in mind, our and we also note that f of x equals 1 upon 1 plus x. With this in mind, we note that our integral value is approximated by h by 2 times f naught, the summation twice of summation f of I going from 1 to 4 plus f of 5. So I have divided the interval 0 to 5 into 5 equal parts as 0, 1, 2, 3, 4, 5. And we have got f of 0 equals 1, f of, I'm writing that value, so it's 1, it's 1 by 2, it's 1 by 3, 1 by 4, 1 by 5, 1 by 6, and this essentially gives the integral the value of half of 1 plus twice of 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6. If you calculate this value, this comes out close to 1.86. which is option B. And finally, we move on to the last problem of the day, and we are asked to calculate this particular integral. I is equal to integral 0 to 1 x upon 1 plus x dx over 6 intervals using Simpson's rule. So here, we are asked 6 intervals. Just draw them here. So this is 0, this is 1, these are 6 intervals of size is 1 by 6. So using Simpson's rule, I can approximate it to be by 3 times f0 plus f6 plus 4 times f1 plus f3 plus f5 plus twice of f2 plus f4, which if you think about it is nothing but a rearrangement of f0 plus 2f2 plus 4f1 plus f2 plus f2 plus 4f3 plus f4 plus f4 plus 4f5 plus f6. So this is what we have, and once you substitute all the values here into Simpson's into our equation, we essentially end up with a value of 0.307. So with that, that covers up the problems that I had for this particular week. If there are no more, if there aren't any more questions for this session, then I'll close this. I thank you for attending this class or watching it online or YouTube.